Hi everyone. So last video we explained, or we looked at the creation of the periodic table, looking at Mendeleev and Moseley. So we see that the initial periodic table was by atomic mass. The current periodic table is arranged by atomic number. And now we can take a look and see the different properties that elements have based on their atomic number, and that periodicity, the repeating pattern, showing based on like what period and group an element is in. We'll see a lot of those. We'll see what properties it has. In order to understand some of these properties we're going to be looking at, there's this concept called effective nuclear charge, which is really saying how much of the positive charge from the nucleus. So remember your atomic structure, you've got your positively charged nucleus surrounded by negatively charged electrons. And so each electron is feeling a certain pull from that positive nucleus. That's why the atom is saying that in the structure it is. But the electrons are also feeling the negative charge from other electrons. So for hydrogen, you've got its one electron has an effective nuclear charge of +1 because there's no electrons around it. Helium, because there are two electrons, each electron is feeling a charge of +2. And this brings us to one of the important points about effective nuclear charge. So the electrons really only are interfering with other electrons on energy levels greater than they are. Electrons within the same energy level aren't really affecting each other. So in period 2, those electrons are some of the positive charge that the second energy level electrons are feeling is blocked by the two electrons in that first energy level, and it's called shielding. When the negative electrons, or when the electrons are basically diluting some of the charge that other electrons feel. So you can see the effective nuclear charge by just looking at the number of protons, because there's always that positive charge is there. It's just being shielded. It's being blocked, and all of the core electrons are basically deducted from that charge. So if you wanted to calculate the effective nuclear charge of a valence electron, you would subtract out all of the core electrons and just pay attention to the valence ones. Remember that core electrons are really the electron configuration of all of the energy levels before it. So for potassium, which is a period 4 element, you're looking at the electron configuration from period 3 and below. So it's really looking at that argon electron configuration. So you've got, in your book it looks at, is it sodium? So sodium has 11 protons, so it has 11 electrons in the neutral atom. And 10 of those are core electrons, because sodium just has the one electron in period 3. The other 10 have to be the core electrons then. So you take that positive 11 charge, and you subtract 1 to get, you subtract 10, you subtract the 10 core electrons, and so sodium's effective nuclear charge is 1. Magnesium, and you can see its group number is also 1. Magnesium has 12 protons, and so it has 12 electrons in the neutral atom. And like sodium, it has the 10 core electrons, so you're doing 12 minus 10, to get an effective nuclear charge of 2. So each one of those valence electrons has an effective nuclear charge of +2. So it's feeling, basically each of those electrons is feeling an additional unit of positive charge than sodium. The reason you're ignoring that one electron in the sodium atom is that there's the valence electrons are really bad at shielding each other shielding each other. They core electrons, because like you can see here, they're below it, so it's really a charge between the outer electrons, and so it can't get in as close as it wants to, because it's also trying to stay away from these inner electrons. But with magnesium, it's not really being affected very much by that other one outer electron, because they can just sort of move around. Like, it would be like if one was here and one was there. So they're not really interfering with each other as much as like this one would interfere with that. And that trend continues across. So then aluminum is feeling an effective nuclear charge of 3, because 13 minus 10. Silicon is an effective nuclear charge of 4, phosphorus of 5, sulfur of 6, chlorine of 7, and argon of 8. And you can see, like before, like with our number of valence electrons, you can tell the effective nuclear charge by that group number. And even on the transition elements, you can't like look at the number and see the effective nuclear charge, but you're still continuing that greater effective nuclear charge as you move across. Because protons and electrons are opposite charges, they're attracting each other. So what do you think a more positive charge, or what do you think a greater effective nuclear charge is going to do to the electrons? So like this electron has an effective nuclear charge of 1, but each of these electrons have an effective nuclear charge of 3. So which electrons would you expect to be closer to the nucleus? It would be the ones that are experiencing the greater effective nuclear charge, because it's a greater positive force, so it's holding them closer and more tightly. So if they're being held more tightly and closer, you would expect that the trends in the size of an atom to follow that pattern of effective nuclear charge. So as you increase your effective nuclear charge, would you expect your atoms to be larger or smaller? We would expect them to be smaller, because since each electron is feeling a greater effective nuclear charge, each one is being held more tightly and closer, and so the atom is going to be smaller. Before we get to the trend in size as we go down a group, there's a caveat I need to make about the effective nuclear charge. So you can see from the way the orbitals are designed, this is looking back at sodium at that the 11 electrons. So we've got our 10 core electrons, and this is just that radial density function. So it's looking at the distance of the core electrons from the nucleus, and this, if you remember the 3s radial density function, sometimes the proton's always in the nucleus. Sometimes the electron is around this distance, and sometimes your 3s electrons are this distance from the nucleus, then there's a node, sometimes they're that distance, there's another node, most of the time they're that distance. So because the electrons are sometimes within those core electrons, the shielding isn't a complete effect, so it's not, the electron isn't feeling just that +1 charge, it's getting to sneak in and get a little bit more of that positive charge, but for our purposes, we can roughly approximate it. All the core electrons, we assume that they completely shield, and then the outer electrons are just getting the shielding of the core electrons, not from each other. One note, so we've been discussing that the effective nuclear charge just of the outer electrons. You could also look at the effective nuclear charge of one of the inner ones. So we'll keep picking on sodium. So sodium has its outer electron has that effective nuclear charge of 1. If we look at sodium, let's look at an electron on sodium's second energy level. Its second energy level, so sodium, we'll draw the Bohr model, it helps see it better. So we've got sodium, so its first energy level, 2 electrons. Second energy level. I like the Bohr model for conceptualizing stuff, but remember, we're the actual model of the atom has the orbitals, the probability density, but Bohr illustrates this point well. So then in our second energy level, we've got 8 electrons. 1, 2, 3, 4, 5, 6, 7, and 8. And we've got our valence electron on the third energy level. Sorry about all the camera motion. Okay, so we saw that this valence electron is being shielded by all 10 of the core electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But what if we want to look at what the shield, what this one's effective nuclear charge is? So remember that electrons on the same energy level really aren't doing any shielding. And in the same vein, electrons farther out aren't shielding it because it's not between the electron and the nucleus. So this is our nucleus, and so this is our center of positivity, and it's what all the electrons want to be near, but they're also trying to stay away from the other electrons. So this electron isn't interfering with this one because it's not between the nucleus and the electron. Likewise, this electron isn't interfering with this one for our purposes. It's a very small amount of interference, so we can ignore it. But it's also not between the nucleus and that electron. The only two between the nucleus and the electron are these two. So here we've got to find the effective nuclear charge acting on one of these second energy level electrons, you've got your total positive charge of 11, because remember sodium has 11 protons. Its atomic number is 11. And we'll take away any of the ones that are between the nucleus and the electron in which we're interested. So if we were working with our third energy level electron, that's why we subtracted 10, because there were 10 electrons between the nucleus and the electron we wanted. In this case, there are only 2 electrons between the nucleus and the one we wanted. So 11 minus 2 gives us an effective nuclear charge of 9. So this energy level is being held tighter than the next energy level. And that concept will be important as we're looking at some of the bonding we'll do. It's part of why you're really only those valence electrons are involved in bonding, because all of these ones are being held much tighter. Like that's being held with an effective nuclear charge of 9. That's 9 positive energy units holding it in place instead of just a 1 for the valence electron. So that's looking at the effective nuclear charge. The other effect, and we saw that the greater the effective nuclear charge as you move across the period, the smaller the atom, because the electrons are being held closer together. The other trend we're looking at is as we go down the period. So remember that what does each period represent? Each period is looking at the number of energy levels. So in the second period you have 2 energy levels, third period you have 3 energy levels, fourth you have 4, etc. So right here we have the Bohr model for sodium. Let's draw the Bohr model for lithium. So lithium, we've got our first energy level with its 2 electrons, and then our second energy level with its 1 electron. And so what do you see between these? So sodium is 1 period lower, it's period 3 instead of period 2, and so it has the 1 more energy level. And you can see, even just from drawing it, there are, with 3 energy levels, your atom is bigger than if you only have 2 energy levels, because as you add energy, the electrons need to be farther away from the nucleus because of the electron repulsions. And so you see here that that's really the pattern. So as you're going down in the periods, or as you're going down a group, you're adding more energy levels, so your electrons are going farther out, they're higher energy, and so you're increasing in size. And so that's those 2 trends we'll see as we look at the other main properties that are going to determine bonding. You're going to have a main trend going across a period and down a group. Those are the two competing effects. And so the first, they're all going to be related to this effective nuclear charge, and a little bit to the size. But the size is a product of the effective nuclear charge, so it's related to the size in that it's determined by those effective nuclear charges. We'll look, now that we understand the effective nuclear charge, we'll explain ionization energy and electron affinity in the next video, since this one might be approaching the limit of uploading.